Lecture. Lecture, bring in office hours. So I'm going to hang around here until 12:30. Anybody has any questions, let me know. I'm just going to sort of hang out here. And yeah, I'm going to pause the video and mute it. But if somebody has a question, throw up a hand, send me a text, let me know. Thank you, everybody who joined me. And then, yeah, Robert.
I had a question about turning in assignments.
Yes, go for it.
Okay, so I think when I was turning in the PLC, I accidentally didn't rename it, but luckily it had the error thing, so it didn't actually go through.
Okay.
But in the future, if I didn't rename it but then remembered, how would I get around? Like, should I send you another one or?
Yeah, just resubmit it. And I think, I'm not 100% sure. I don't know. Can you delete a file that you've already uploaded?
I'm not sure.
Okay, so then I would just say, if you forget, just upload it again. I won't take off points if you do have the correctly named one there.
Okay, thank you.
You're welcome. Rosa, question.
Do you hear me?
I can hear you.
Okay, I have a question about the homework.
Okay.
Exercise 44.
So wait, this is homework for chapter 9?
No, chapter
I'm sorry,
10.
Chapter 10?
Chapter 10, yes, please.
All right, let me, what's the easiest way, let me close this for a second. See if I can open up OneNote with chapter open. Chapter 10 and exam part lecture notes. Chapter 10 problems. Oh, look at me. All right. Let me share the screen. Okay, chapter 10, which problem?
44.
Problem 44. It's been a great day of new frictionless snow. Julie starts at the top of a 60-degree slope shown in the figure. At the bottom, a circular arc carries her through a 90-degree turn and she launches off a 3-meter high ramp. How far horizontally is her touchdown point from the end of the ramp? Okay, what's your question?
I got the final velocity when it is when it's at the point of the curve, but after that I'm like, I don't know what to do when it is.
So just to be clear, you use conservation of energy to figure out how fast Julie's going as she's leaving the ramp?
Yes.
So you just said that her potential energy at the top, well, you just basically use the kinetic plus potential energy as a constant?
Yes, I did.
Okay, and I don't have the answers with me, but you've got how fast she's leaving the ramp at.
Yes.
And what is that speed? Just
20.7 meters.
Okay, so now this is a completely separate problem as basically a projectile motion problem. So the 20.7 meters per second at a 3-meter elevation. So let me do a, so now the problem is, actually let me look at this, 3 meters, 60 degrees there, 60 degrees. Okay, so a couple things that you need to know for this. Let me stop that again. Share screen. So now, in essence, you have a projectile motion problem where it's being launched from a height of 3 meters. You found that the initial speed was 20.7 meters per second.
Yes.
And the angle here, let me go back to that. Oh, all right, can't share this. So the angle is going to be, let's stop the new share, go back to this. So if that's a 60-degree angle, that angle there is going to be, let me double check something real quick. Physics 4A, how much?
Yes.
Problem 40. Okay. How do I go back? Screen sharing is paused. Stop share. Okay, so one, just so you know, the problems that I give for the celebration can't be this involved just because I'm not giving partial credit and it's going to be, you know, relatively simple. But the key here is, so you use conservation of energy to figure out this, correct?
Yes.
So now, without going sort of into the trigonometry, and I wouldn't ask something this involved, but you can show that the angle that they're leaving the ramp at is 90 degrees minus 60, it's 30 degrees. So now
Okay.
this basically just becomes a projectile motion problem with something being launched at an initial height of 3 meters, initial angle of 30 degrees with an initial speed of 20.7 meters per second. So you could figure out V naught X, which would be V naught times cosine theta, V naught Y, which would be V naught sine theta. And in essence, what you're going to need to do is figure out the time in air from the vertical motion. And here's a case where something is being launched at a different height than it lands at, which means you're going to have to solve a quadratic equation. So what you're going to end up solving is you have y equals y naught plus v naught yt plus 1/2 ay t squared. So my y naught in this case would be 3 meters. My y would be 0 meters. My v naught y is going to be whatever v naught sine theta ends up being. I know what my acceleration in the y direction is. And so you have a quadratic equation to solve for time. Once you have that, that's how long it's in the air for. And then you can use x equals x naught plus v naught xt to figure out how far it goes. So your v naught x is just going to be your v naught cosine theta. The t is just going to be the time that you get by solving the vertical motion for the time in the air.
Okay. Thank you.
Yeah. So, you know, this would be a typical problem that I would probably ask on a final if we had, you know, the full 3 hours and everybody was taking this on campus. Probably wouldn't ask something with multiple steps like this for the upcoming celebration.
Okay.
But
Thank you.
if you got the whole initial velocity from conservation of energy, that's the most important part.
Okay, yeah, I was just confused like how to get yeah, I just forgot about the quadratic formula in order to get time.
Yeah, so keep in mind if you're solving for the time in air, anytime something lands at a different height than it's launched at, you can't use the time in the air as twice the time to the highest point. You're pretty much going to have to solve a quadratic equation to get the time.
Okay, thank you, Joe.
You're welcome. Kendra, Adrian, you guys have a question? Adrian.
Yeah, I had a question about the lab. That is lab number 9. I did all my results, and my averages were pretty consistently. The experimental averages were pretty consistently about 0.1 for below the theoretical average. I'm wondering if that is to be expected, or the theoretical value.
Are you talking about for the acceleration and the tension?
For parts 2 and 3, for the kinetic energy, the kinetic energy final.
Right. So did you get that the final kinetic energy was less than you expected from the initial energy?
Yes.
That's what we would expect, because in this system, we're ignoring air resistance, we're ignoring friction. So any work that's being done, we're kind of ignoring the fact that thermal energy is being generated. So
okay, excellent. Thank you.
So one thing you could do is the difference between the energy it starts with and the energy it ends with should be the thermal energy generated. So one thing I thought about doing as a lab was you could actually estimate what is the coefficient of friction, because, let me just share the screen. Erase all this. Where's, I want to clear everything. So if I said my initial, what am I doing? So the work done by all external forces is basically equal to the change in energy of the system, which in this case, we were just looking at the change in kinetic energy plus the change in gravitational potential energy. So I was kind of saying my initial kinetic energy plus my initial gravitational potential energy plus any work done by external forces equals my final kinetic energy plus my final gravitational plus any change in thermal energy. Well, the way we defined our systems, we were ignoring air resistance, ignoring friction, and so the work done by external forces was 0. So in essence, this is my initial energy, this is my final energy, but we also ignored thermal energy. So the difference between the energy I end up with and the energy I started with should be how much thermal energy changed. And so if I were to calculate that, say my change in thermal energy equals my initial total energy minus my final total energy, I could, oh, I don't like using that E twice. Let me erase this for a second. Eraser. So the change in thermal energy should be equal to my initial total energy minus my final total energy. So you're not doing this, but kind of an interesting thing. You could figure out, okay, what's the difference between the energy I started with and the energy I finished with? That difference should all be because of thermal energy being generated. And I know the change in thermal energy is equal to the force of kinetic friction times the displacement. And in this particular case, the normal force is just going to be equal to the weight, mg. So I could get that the force of kinetic friction is mu k mg. So I could, if I wanted to, try and solve for what is the coefficient of kinetic friction from this experiment. I didn't do it myself, but that was a long about answer. The answer is I expect the answers not to be consistent because I'm unrealistically ignoring air resistance and friction, both of which are present.
Okay, excellent. Thank you.
You are very welcome. Let's stop that. Hey, Kenny, any questions on your end? When the poll disappeared on my screen, here's what I did. Alt-Tab, hold down the Alt key and tap the Alt-Tab to bring up small, oh, running, and then toggle through them. I ran through them and stopped on the Zoom meeting to bring it up. Thought this, oh, so wait, Alt, why can't I find Alt? Oh, Alt-Tab, or Alt space, Alt. Oh. Hey, that's a new thing I learned today. Bonus points for you, Kenny. I'm writing that here, Alt-Tab. Thank you, thank you, thank you for that. Kenny, you have any physics questions I can answer? Thanks, Joe. Yes, but not yet. All right, I'm going to hang out here for another 5 minutes or so. Let me know if you have any questions. Let's get that. I'm going to pause the video. Oops. All right, it looks like that is the end of office hours. Thank you, Joe. You're welcome, Joe. You rock. You rock.